Okay, so welcome back to this next video in which we are discussing glycolysis. Okay, so we've discussed the first reaction of glycolysis, in which you take a glucose molecule, which we've agreed is what we will call, what is strictly called an alpha-D glucopyranose molecule, and what we're going to do is add a phosphate group onto the alcohol group of the 6th carbon of that glucose molecule to create what we will call glucose 1-phosphate. And this reaction requires you to invest an ATP molecule in, okay, and degrade it down to an ADP molecule, because we're cutting off that gamma phosphate group off the ATP molecule and putting it onto the alcohol group of the 6th carbon of the glucose molecule. And there are two enzymes which can catalyze this reaction, which are called hexokinase and glucokinase. And importantly, this reaction is one way. You cannot undo this reaction, okay, at least not through one of these enzymes. Okay, right, so next reaction up. We are going to now convert glucose 1-phosphate oh, whoops, sorry. Let me just take this back. This is not glucose 1-phosphate. I do apologize. This is glucose 6-phosphate. Okay, that's a terrible mistake. Right. And we're going to convert glucose 6-phosphate, and it's called glucose 6-phosphate because the phosphate group is coming off the 6th carbon's alcohol group. Okay, and we're going to convert glucose 6-phosphate into what is going to be called fructose 6-phosphate. So I want to show you the structure of fructose 6-phosphate. Okay, and then I'll try and explain the reaction that is going to happen. Okay, so this reaction is going to be reversible. It's going to go both ways, and it will be catalyzed by one enzyme both ways. Okay, so basically what we're going to end up with is fructose, and fructose again, strictly speaking, fructose is the name for a linear version of this, but we won't go into that too much. The normal form of fructose is the cyclic form. Okay, so we have our 5-membered ring here, like so, and then what we're going to have is we're going to have a group coming off here and a group coming off here this time. Okay, and both of these groups are going to have alcohol groups coming off them, and this one is still going to have a phosphate group coming off it, like so, because effectively this is the same carbon as we had over here, and it's got the same 6th carbon coming off up here with the same phosphate group coming off. Okay, so this is why this is called fructose 6-phosphate, because off the 6th carbon's alcohol group you have a phosphate group, and we're sticking to our same notation as always. Going up means that it's coming out of the page towards us. And then we also have this new carbon over here, which is odd, but this is in fact the same carbon as we had here, and it's got an alcohol group coming off it. Okay, right. Now, we've also got an alcohol group coming off this, which will be going down because it's going into the page away from us. So this first carbon here is coming out of the page towards us, and the alcohol group is going into the page away from us. Now, the alcohol group here will be coming out of the page towards us, and the alcohol group here will be going into the page away from us. So this is the structure of fructose 6-phosphate. Now, how did we go from this to this? Well, basically what we did, and this isn't meant to be an electronic mechanism, this is just to make sense of the reaction. What we did is we broke this bond between this carbon and this oxygen. Now, in a covalent bond, you have 2 electrons, one from each of the 2 members of the bond. So imagine giving the electron from the oxygen back to the oxygen, and the electron from this carbon back to this carbon. Now, what you're going to do is move the whole thing up. So you're going to move this carbon up and bind this carbon to this oxygen. Now, at the moment, this carbon's fully saturated. It's got an alcohol group coming off it. It's got a hydrogen coming off it. It's got these 2 bonds here. So what you're going to do is you're going to take off that hydrogen. So I'm just going to break with the skeletal structure for a moment and show the hydrogen which is coming out of the page towards us. Basically, what you're going to do is you're going to break this bond between the second carbon of the glucose 6-phosphate molecule and the hydrogen, okay? And imagine giving one of the electrons back to the hydrogen and one back to the carbon, okay? Now, take this hydrogen and bind it to this carbon up here. So remember, I've just broken this bond between the oxygen and this carbon, so that means this carbon now has a free electron. We can bind that free electron to this hydrogen, okay, and saturate this carbon once again. So now it's got two hydrogens coming off it. It already had one and it's been given a second, and also an alcohol group. So that's what has become this over here, and I might just highlight it in. This green here is now over here. So it's got two hydrogens coming off it and an alcohol group. So note, it's no longer a chiral center because it's got two hydrogens coming off it, okay? So we don't have to worry about optical isomerism up there. Now, this carbon has a free electron because of the breaking of this bond, and this oxygen has a free electron. We will bind this carbon to the oxygen, okay? So it becomes this carbon here, okay? And then just to emphasize things even more, this carbon here therefore becomes this carbon here, and this carbon up here becomes this carbon down here. And then we've already discussed that this one is equivalent to that one up there. Okay, so that now explains the directions which these alcohol groups are going in. This one is going into the page because it went into the page here. This one is coming out of the page because it went out of the page here. This alcohol group here is going into the page because it went into the page here, and then this methylene group with the alcohol group off has been forced to come out of the page towards us. Okay, so that's where this molecule comes from. So we didn't need to bring any extra molecules in. We are just changing this molecule. We didn't bring in anything. All we did was change what we've got, basically. So we changed it. We changed the structural isomerism of it, basically. Okay, so this reaction firstly is reversible, okay? It goes both ways, and it's catalyzed by an enzyme which is called phosphohexose isomerase. Okay, so phosphohexose isomerase. So both of them have got 6 carbons in, so that's why they're known as hexoses, because they've got 6 carbons in, and both of them have got a phospho group, so they're both phosphohexoses. Okay, and then we're changing the structural isomerism of them, so this is phosphohexose isomerase. Okay, right. So what's going to happen is we change glucose firstly into glucose 6-phosphate via either hexokinase or glucokinase, and then this enzyme phosphohexose isomerase is going to turn glucose 6-phosphate into fructose 6-phosphate. Now, the next step is another irreversible reaction, okay? And what we're going to do now is we're going to add a phosphate group onto this alcohol group in exactly the same way as we originally added a phosphate group onto the alcohol group of the glucose molecule, okay? So we're going to use ATP again, so this is going to be another investment step where we are putting ATP in the hope that we will get a good payoff for it later. Okay, so we're going to take fructose 6-phosphate, which is often abbreviated just to F6P, okay, and we're going to convert it, let's show the structure of this next molecule, into fructose 1,6-bisphosphate, and this, again, is an irreversible reaction. So all of the investment steps where we are using ATP molecules to stick phosphate groups onto things, these are irreversible, basically. Okay, and the enzyme which catalyzes this is a very famous enzyme, phosphofructokinase 1, or for short, phosphofructokinase 1 is often abbreviated to PFK1. So phosphofructokinase 1, or PFK1. Okay, right. And this is the reaction that usually most people can remember is irreversible because they remember the enzyme phosphofructokinase 1. Okay, so basically it's going to stick a phosphate group onto that alcohol group of the first carbon of fructose. Okay, so let's draw out our fructose 5-membered ring again. Here it is. And then we know that we've got these carbons coming off this one, and they're coming out of the page towards us. We know also that off here we have an alcohol group going into the page away from us. And now off the alcohol group here, the new thing is that we've stuck a phosphate group here, which wasn't there before. Okay, and then we want the optical isomerase in here. The alcohol group comes out of the page off here, then it goes into the page off here. Okay, and then there's no alcohol group coming off this one here. Right, and now all we need to do is complete what we already had, which was that we had a phosphate group coming off this 6th carbon up here. Okay, so this molecule is now called fructose 1,6-bisphosphate. So we've got fructose, and then we've got phosphate groups off the 1st carbon's alcohol group, and also off the 6th carbon's alcohol group. So this is fructose 1,6, and then it's bisphosphate for 2 phosphate groups. Okay, so fructose 1,6-bisphosphate. Right, and that conversion from fructose 6-phosphate to fructose 1,6-bisphosphate is an irreversible reaction. Okay, so the next reaction then, and we're still in the preparatory phase of glycolysis. This is going to be the final step in the preparatory phase of glycolysis before we then go into the payoff phase. Okay? In the final stage of the preparatory phase, you are going to split fructose 1,6-bisphosphate into 2 separate molecules. Okay? And again, this reaction is incredibly reversible. Okay, so it goes both ways, and it's catalyzed by an enzyme known as aldolase. Okay, so let's see what is going to happen. And by the way, aldolase is sometimes also known as fructose 1,6-bisphosphate aldolase. That's just a longer name for it. Okay, but often people just call it aldolase. So basically, this is where I stop drawing skeletal structures and start drawing molecular formulae. So we'll take this slowly. So we're going to start off with a molecule that we get from this portion over here, basically. So let me show you what's going to happen. So I'll draw the molecules that we're going to get first, and then I'll show you how we get them. So this phosphate group is coming from here, basically. Okay, so here it is. Then we have a carbon here, and now I'm suddenly going to start drawing this carbon as a carbon with 2 hydrogens coming off it. So here we go. Okay, then we get this carbon here, and basically we also take this oxygen here. So one of the things you're going to do is you're going to break this the single bond here between this oxygen and this carbon. Okay, and imagine again, and I'll stress that this isn't an electronic mechanism. I'm not trying to show you step by step how the electrons move. I'm trying to make the reactions make sense. Okay, I'm showing you how what's on this side adds up to what's on this side. Okay, so imagine giving 1 electron back to the oxygen and 1 back to the carbon. So this oxygen currently has a free electron, but it's attached to this carbon here. So in fact, it might be helpful to circle the carbons again. So this has come from here, okay, in blue there. I'll show in green. This one here has come from, this one here has come from there. Okay, and that's where it's got this oxygen from. That oxygen came from here. Then it also had a hydrogen off that wasn't previously shown. And then finally, it's going to have this final carbon over here. Okay, so we're going to take this carbon down here. And again, what you're going to do is you're going to chop the bond between these 2 carbons here. And again, you can imagine sending 1 electron back to each member of that bond. Okay, so that will give this carbon a free electron. Now imagine breaking the bond between this oxygen and this hydrogen here. So we had an alcohol group off this orange carbon, but imagine breaking the bond between the oxygen and the hydrogen. Okay, so give 1 electron back to the oxygen, give 1 back to the hydrogen. Now, this carbon here had a free electron from the breaking of this bond. This oxygen now has a free electron. They're going to turn this single bond into a double bond. Okay, so you'll get a double bond here. Okay, now this carbon also had a hydrogen coming off it that was coming out of the page towards us that I hadn't previously shown. So the carbon's now perfectly happy, and so is this oxygen, But we've got this free electron hydrogen here that's got a free electron. We'll stick that onto this oxygen here to create a valid molecule, basically. Now, what is this called? This is called glyceraldehyde free phosphate. Okay, so let me just explain to you why it's called that. Okay, so basically it's called that because it's based on the structure of glyceraldehyde, and to understand why glyceraldehyde is called glyceraldehyde, we need to know what glycerol is, because that's the starting point for all of this silly naming. Okay, so let me show you the structure of the molecule glycerol. Okay, so glycerol is a free carbon molecule where each of the carbons has an alcohol group coming off it. Okay, like so. So the official name for glycerol is propane 1,2,3 triol. Okay, and that tells you that it's a free carbon molecule with alcohol groups that come off each of the carbons. So this is glycerol. Now, basically, if we want to turn glycerol into glyceraldehyde, what we do is we take one of these carbons on the end, and instead of having an alcohol group off that, we put an aldehyde group there. Okay, so glyceraldehyde then is again a free carbon molecule, but you have an aldehyde group right at the end here. Okay, and then these two carbons here still have alcohol groups off them. So this then is the structure of glyceraldehyde. And hopefully now we can understand why this is called glyceraldehyde free phosphate. Because we do actually have this glyceraldehyde molecule within this structure. Here are these free carbons here. So if I draw the analogy, this one's the orange one, and this one's the green one here, and this one's the blue one here. And we have alcohol groups in the correct places. So for instance, this alcohol group matches this one, this alcohol group matches this one, except that we've added a phosphate group onto this third carbon's alcohol group, because the way you name the carbons is the one involved in the aldehyde is number 1, then 2, then 3. So this is glyceraldehyde free phosphate. So that's that molecule sorted. Now, of course, we need to acknowledge that we're going to get another molecule from this as well. So let's have a look at the other molecule that we get from this. Okay, so the other molecule is a little bit more difficult to understand how we create it. So basically I'll show you what we get, and then I'll show you how we get it. So the next molecule is something known as dihydroxyacetone phosphate. So it's dihydroxyacetone, and then it's phosphate, and for short, dihydroxyacetone phosphate is often abbreviated to DHAP. Okay, so let me just show you the structure of acetone, then we'll infer what the structure of dihydroxyacetone is, and then we'll get what dihydroxyacetone phosphate is. Okay, so the structure then of acetone is, again, it's a free carbon molecule where you have a carbonyl group in the middle, okay, and then you have methyl groups coming off either end. So here's a methyl group, here's another methyl group. So this is the structure of an acetone molecule. Okay, now if you want dihydroxyacetone, this thing here, what you do is you put alcohol groups off these two carbons. So for instance, you'll put an alcohol group off this carbon and an alcohol group off this carbon. To turn this into dihydroxyacetone phosphate, what you then do is put a phosphate group off one of those alcohol groups, okay? So here is the free carbon structure of acetone. We'll then have these alcohol groups coming off both sides, hydrogen here, and what we're going to do is link a phosphate group to one of these alcohol groups via a phosphoester link, and we'll choose this one. Because of the symmetry of the molecule, it really doesn't matter which one I put it off. Okay, so that's the structure of dihydroxyacetone phosphate. So some bits of this are very easy to understand. For instance, it's easy to see that this carbon here is going to have come from this carbon here, because we've got a methylene group and then the phosphate group off. Now, we need to somehow figure out where we get this carbonyl group from. Okay, so we've got an oxygen off this carbon that must correspond to, and I need to get another colour. This one in red This carbon here must correspond to this carbon here. And we've got an alcohol group, so we must turn that into a carbonyl group, just as we did down here. So what we have to do then is again split the bond between this oxygen and this hydrogen, like so. So what you'll do is give one electron back to the hydrogen and one back to the oxygen, okay, or at least that's how we can make sense of this. Of course, that's not how the electrons will actually move. Homolytic fission is something that creates free radical chain reactions, and you're not going to get one of those happening here. But to make sense of the reaction, it's the easiest way to go about this. Okay, now this carbon already has a free electron because of the splitting of this bond between the oxygen and the carbon here, so we can then bind the free electron of this oxygen to this carbon to create that double bond here. Then all we have to sort out is the free electron of this hydrogen, but of course we had a free electron off this carbon down here, so the final carbon. Now I'll have to use yellow. Okay, so here's yellow, is this carbon. So we've got our alcohol group, which is here. We've got a hydrogen already, but this carbon has a free electron because we broke this bond between this carbon and this carbon. So we can then attach this hydrogen, which has a free electron, to that carbon, which has a free electron, to create dihydroxyacetone phosphate. Okay, right. We'll call it there for this video, and then we'll continue the story where we'll look at the pathways for these two molecules in the next video.